Welcome everybody to our PyMC Labs webinar with Tarmo, Alex, and myself. Today we're going to talk about a candle in the dark, how to use hierarchical post-stratification with noisy data. And with me, the people who have actually worked on this, and we're going to hear about what that is about and the technical challenge we had to overcome working on this. Just a few general notes. So I'm Thomas Wiecki. I worked in PyMC a lot. Now we founded PyMC Labs. And of course, this is the project that we worked on is in this vehicle of PyMC Labs. And what do we do? So we are the Bayesian consultancy, and the team that we have assembled basically emerged out of the PyMC core developer group. So we developed the software over 10 years and have a really rich ecosystem of contributors and users, and a subgroup of us have banded together to launch the Bayesian consultancy and help companies take their PyMC models to the next level or develop new PyMC models for them. And I couldn't be happy about the team that we have assembled. We sometimes call ourselves the Bayesian Avengers, and that's how we'd like to be remembered in the future. Yeah, and we have a team of various backgrounds, and Alex, for example, has a background in political science, so that will be very relevant here. In the industry, we work on all kinds of different problems. A lot of them actually marketing problems. For example, what is the expected future revenue for a customer? And of course, as we're Bayesians, you see that there's a whole probability distribution over that, not just point estimates. A lot of times we encounter spatial data where you want to model the distances between that. So if you have a marketing campaign, probably neighboring countries will react similarly to that. Recently also, we've gotten quite interested in causal inference. So for example, if you want to know what the causal impact of a marketing campaign is, towards this, we have recently released a new package called Causal Pi. If you go to PyMC Labs.io, you can see a blog post about this new package that combines Bayesian modeling with causal inference. Or media mix models. So these often are used in marketing if you want to understand better where your marketing dollars are going and how that is driving new users signing up to your website. Here's a bunch of links. I'm going to also post these in the chat, but check out PyMC and PyMC Labs on Twitter. We have a code of conduct that you can check out. And then the last thing is we also have an online course. So this is a self-paced online course with Alex Andorra and Raveen Kumar that you can check out at intuitivebase.com. And we try and abstract away all the math and really just focus on the application and the coding aspect of this. So that's it for the intro. Next, I'd like to hear from our esteemed guests. Tarmo, could you introduce yourself?
Yeah, sure. My name is Tarmo Jüristo. I come from Estonia, so we have a small foundation. I'll talk in a moment. I'll talk a little bit more about that. While we got set up about 2 years ago, and working with the data. Again, I'll be talking about more about that in a moment. But I soon enough came across of one interesting fella keeping a learning Bayesian stats podcast and putting out models about elections in municipal elections in Paris, or the popularity of French presidents, and this seemed to be very close to what we were trying to do. So I ended up reaching out to Alex. And interestingly enough, found out that he was in Tallinn at the same time when I first got across. So we got together, we figured out if there's a scope of working together, and we ended up hiring PyMC Labs to put together the model for us. And today I'll be showing you a little bit of where we ended up in about half a year. So we ended up working on this from start to finish, from the first contact to the model being delivered. It took about 6 months altogether. So, but let's go to the my notes. So let me try and find. So here we go. This should be it. Okay, so I hope everything's visible. I don't see the shared screen. So I believe this was Alex who came up with the line, the candle in the dark. So we'll be having a very romantic sounding presentation. So we I guess Alex can later say what he actually meant about this, but I can only guess that it must refer to trying to make inferences in a uncertainty, trying to get something out of a flickering flame of a little bit of data, and to walk into the light of knowledge with this. So let's see how it worked out. So first of all, like I said, Salk is a foundation for progressive politics. There are a few of those around the world in different places. We do actually a few more things than just this, but pertinent to our today's discussion is that we're aiming to provide quality data with accurate and actionable analysis to progressive political forces in Estonia. And for this, what we do is that we actually do use a lot of different data sources, but the mainstay or the bread and butter of what we do comes from monthly polling data on political preferences. So it's we work a lot with the quality. So it's the data we use post-stratification weighing to get the data representative for the population we're looking at. We have lots of different data dimensions to the data points, about 45 different dimensions, not all of them independent, but anyway. So what this gives us, it gives us a very good top line view. So if we want to know anything about people's party preferences, people's political preferences over the whole population, then the visibility is actually very good. We are pretty happy with the way how it's running. You can take a big slices, like say, okay, I'm interested in what men versus women think of certain things. But as we're working with data, and the data is always limited, then the visibility gets a lot worse as soon as we try to zoom into any specific groups and dimensions. And just to give you an idea, so normally we run our monthly polling rounds are with a sample size of 1,200 people, 1,200 people. So that's good enough to give us across the population the sorry for using now the frequentist lingo here, the confidence intervals of it gives us a confidence of plus minus about 1.52 percentage points. However, now if we zoom in, if we apply just 3 simple filters, say that I'm interested in males, I'm interested in non-Estonians. So there's about a quarter of the Estonian population is Russian speaking. So let's say I'm interested in them, and I'm interested in people in the second largest city in Estonia, which is Tartu. So then by applying these 3 filters, the initial 1,200 will shrink to 4 observations. So this is the problem then. And it's not, I could go on and adding these slices and filters, and it's becoming smaller and smaller. So this is the nature of the problem. And if I'm trying to make any inferences, or if I'm trying to make any points about, what the Russian-speaking men in Tartu might be thinking or preferring, then, on a monthly basis, I would be just operating with 4 or 5 observations. And clearly, this is not enough for making any statements or any claims. But maybe it is, because the trick there, and to explain what we're about, then when I'm trying to explain it to laypersons, people who are not, working with Bayesian models every day, then I start normally with, the old mildly chauvinistic blonde joke. And as the joke goes, is that the blonde gets asked that what is the likelihood of meeting a dinosaur in a town hall square? And, as you can guess, the joke comes from the fact that the blonde answers it's 50-50. I either see the dinosaur or I don't. And then you would go, ha, 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 and say that, what a silly person. But, this is actually a correct answer, given if you do not know anything about the town hall square or dinosaurs, then you should not have any other preference. Then you would have what Bayesians call a flat prior. You'd say that, yeah, it's I have no idea if I do see a dinosaur or no. And of course, the butt of the joke, or what makes it supposedly funny, is that we do know quite a bit about dinosaurs, and we also know what kind of fauna we can expect to meet in a town hall square. And putting these two things together, we say that it's just a silly. It must be a really silly person who thinks that it's 50-50 seeing a dinosaur in the town hall square. And now coming back to the issue at hand, the point that I'm trying to make with this joke is that. If we say that we cannot, if we say that we only have 4 observations of Russian-speaking men in Tartu, and we can't say anything about them on that basis, then we are like a blonde who says that, it's 50-50 whether we see a dinosaur or not. Because that would imply that we know nothing about Russians, we know nothing about men, and we know nothing about people in Tartu. But in fact, we do know a big deal about all these three relevant dimensions. And, this is where the magic of the Bayesian modeling would come in, that we can use what we know. We can build a model that learns across these dimensions and gives us a pretty good guess or estimate what the end result might be after applying these 3 filters. And the way you go about this is that this now goes into a bit of a domain knowledge about the politics. So in our case, in the Estonian case, we have found out that people's political preferences are influenced or, to a large extent determined by these 4 dimensions. So it's education, nationality, age, and gender. The importance of those varies from question to question. In many cases, the nationality comes first and then makes the biggest impact, and then you would go into gender and education based distinctions. And in some cases, you would want to use interactions between these. So for the simple reason that, for instance, education is not distributed the same way across 2 different genders and so on. So you may want to work with a bit more precision in some of the cases. But basically, this is what gives you this framework of working with the survey data. In the US case, you would have a race again instead of nationality, and you would definitely have to add religion in US case, which is not an important distinction in Estonia, but that would work pretty much the same way. In a fundamental way, it would be the same. So, and because we do have for every data point, like I said before, among those 40 different dimensions, we do have age, education, gender, and nationality, then we can plug those in and build what's called the MRP, or the multi-level regression with post-stratification. So this is the model we ended up building with the help of Alex, or actually Alex ended up building it with our help. And just to unpack it a little bit. These 3 letters MRP, if we start with the R, then what the regression part of the model does, and again, Alex is definitely more qualified about talking the inner workings of the model than I am. I'm just trying to give a broad picture, broad overview, is that it picks up the signal across those different dimensions that I mentioned, these 4 main ones, and some of the interaction effects that we put in that seem to help the model over the whole data set. So it learns which way how your education impacts or affects your party preference or whatever preference you might be interested in eventually. Then the multi-level part is where we stratify between different localities. So we actually have a three-level model. It's kind of like a Russian doll of getting into a broader categories. And the model can differentiate or stratify between these different levels while learning from all the available data. And then finally, with the post-stratification part, what we do, the simplest way of putting it is that it scales the model result to the actual population. So there's a more technical way of explaining it is that we take the census data from the statistics port. Estonia luckily had our national census at the beginning of this year, so we had very fresh data. So this gives us all the strata of how many people of certain nationality, certain age, and certain education is there in any cell of geographic location, and then we can take the signal that the model learns from the data and basically simulate the whole population and scale the result over it. So this is the MRP in a nutshell. So the way it works, the way it's put together. And on top of it, we ended up adding some of the stuff by our own. So this was, I should say straight away that this was one of the main advantages of working with PyMC, just like Thomas said before. Those are people who have been building the tool that we're using for modeling. And so this was my prior was that these people know how to actually put together a firm foundation for the model, and it ended up being exactly the way I expected. So we got a very solid, very efficient, very quickly running model, so that we could easily go and expand it. We could add a component which predicts the election turnout based on the previous elections data. So it's just, you make a component and plug it into the model, and it just, samples a little bit longer, but everything works fine. Then we added the Gaussian process component, which made the model time aware. So if I'm not going to be dwelling too long on the Gaussian process here, but if somebody wants to hear more about that, then drop a question and we can come back to that later. So this is actually a pretty significant addition and very significant advantage you get by making the model time aware. We also added the bit where we, instead of when you try to model or predict the people's party preferences, then those tend to be independent of each other. I mean, those are, categorical variables, which are not, there is some covariance, but they are not, strictly linked to each other. However, if you want to ask people, for instance, what do they think about immigration, or what do they think about climate change, then you would normally go and ask that on a Likert scale, saying that, people's, they have opinions that are strongly in favor, rather supportive, they have slightly against, or strongly against. And this is the ordinal scale, so you can use that because, the difference between strongly against and relative or slightly against is smaller than the difference between strongly against and strongly in favor. And that will help the model, that will help your inferences, and gives you, it's a broader point that, the kind of the model we're talking about here, we initially set it up, or initially made it so that it will predict, or it will recover from the data the latent support for the parties, because this is very easy to validate, easy to check against the ratings that are constantly being put out, but it can be used for basically whatever question you want to ask, where you have those 4 relevant dimensions plus the geographic location. And you can zoom into pretty amazing stuff with this, but we'll be coming back to that later on briefly. Then let's go to the model output. So for people who are familiar with the PyMC modeling, then this looks different from your normal Arvis trace plots and everything else. So this is what we implemented, fitting into our own workflow. So much of it is in Estonian. The variables are still in English from the time when we were working together with Alex on the data, so I haven't put it back into Estonian. But here you can actually see I took the same strata that I used at first, making the point where, if you remember, that was 4 observations. The gender male. Gender is stratified here, so male is up here. The district is Tartu linn or Tartu city, and the nationality is not Estonian. And so this is what the model allows you to pull out, basically on a basis of 4 observations, although it's exactly, if you say that it's just 4 observations, then you're being a blonde saying that it's a 50% chance of seeing a dinosaur. So this is the data that model extracts from, or this is the signal that the model extracts from the whole data, then picks up relevant dimensions of geographic location, nationality, and gender, and then by magic of post-stratification scales it to the city of Tartu and these dimensions, and gives us the indication. Now, I trust most people are probably at least vaguely familiar how to read the box plots, but I think there's a good point to be made here about what kind of a signal you would expect from the Bayesian model in that sort of situation. So obviously, of course, like Thomas was saying in his first notes on a different topic, Bayesian models do not give you point estimates. So this is not something you should be after in these cases. They give you sampling ranges, and box plots display them. So the whiskers cover the whole sampling range. The boxes inside cover inner 2 quartiles, and the white line gives you a median of the distribution. So basically, if I'm trying to make this point and talk to politicians, people running campaigns, whoever else is interested, then what I'm saying is that this is not a crystal ball. This is not something that tells you what every single Russian male in Tartu would happen to be thinking, but it gives you a pretty good indication that if you were to make a bet or accept a bet, that observing females, Russian-speaking females on the streets of their city of Tartu, then would you be making more money by betting on EKRE or betting on Keskerakond as their party preference? And this is where the model pretty firmly tells you that you will definitely make more money by betting on Keskerakond than on EKRE here. Does it mean that you can't lose a bet on betting on Keskerakond? No, you can. You definitely can, because there's a sizable part of population who do in fact prefer EKRE. But if you were making bets, you can be very confident that you'll be making money by placing your dollars or euros or whatever on this choice. And however, at the same time, if you were ask the same question, would you prefer, in case of males, would you prefer EKRE to ST200? Then, the model would tell you that this is pretty much coin flip. So if you had to make a choice, then the model would slightly steer you towards ST200 in this case. But, basically the answer is that it's a coin flip. So you would be betting on a pretty thin margin there. And now this is an important point to understand about the variance, how confident you should be. Just to give you an example, then, or the different view, if we disregard the Tartu city and look at the whole population, then you will see that suddenly all the the ranges become much more narrow because there's a lot more data, and the population you're talking about is much bigger. So the model becomes a lot more confident in in its ranges and estimates, and that's how it should be. And again, this is a nice view because we can easily validate it against the ratings with surveys run with pretty big samples, and it was thrilling to see that the model can pick up the signal really well. It can pick it up also with even in the absence of data. So you can have no observation. I can throw up all the observations of city of Tartu, and model would still give me a pretty good estimate on the basis of the hierarchical structure, the rest of the data, and priors. So it seems to be working quite well, and we are quite happy with this. However,
one quick question from the audience that I think fits in well here. So
okay.
Gabrielle asks, on the multi-level aspect, it was briefly stated was like a Russian doll and based on localities. Does this mean you modeled clusters groups within other clusters? If so, what were these clusters / groups?
Alex, do you want to take this one?
Sure. Yeah. Yeah, basically that's that. Here in that model, we have 3 levels. So Estonia, so national level, and then we have electoral districts level, and then we have the units level. But I mean, here it could be also nation, region, city, for instance, right? If that's more something you're more familiar with. So yeah, that's basically that. And what the hierarchical structure does is it's modeling. So the observations are at the lowest level, so the unit level. So it's modeling at the unit level, but then it pulls all that information to get information across electoral districts. I mean, across units per electoral district. And then once the model has estimation per electoral district, it also looks at the highest level, which is just one big estimate at the nation level. And that also goes backward. So that's the forward pass. And then you have the backward pass where once we have estimated national level, that also gives us information about electoral districts and how far from the national average each district is. And also depending on how much data we have in each district, then the model will pull this electoral district more towards the national average. And then the same process happens at the lowest level, which is the unit one. Yeah, so I could dive way deeper, but that would start being a bit abstract. I'm happy to answer even more precise questions if you guys have some, but I think that's already an answer to your question.
Okay, and there are a few more questions. I put it open as well. So the easy one to answer is Tom. Yes, this is Streamlit. We use Streamlit throughout our workflow. So we will probably later be showing the same thing live as well to you. So the GP and interactions, we can come back to those in the Q&A part. So I'm happy to talk more about this, but let's go through the main part and then come back to that in questions. So where were we? In here. So the model output is a posterior, so it's inference data object. So this is something that has a lot of different stuff in it. But what we do on that basis is that we feed it into subsequent steps of our data workflow. So it gives us the latent support of parties along any dimension, like we said before. Then we modify this latent support by propensity vote that gives us the likely turnout by party. Then we feed it into a simulation that predicts the vote shares of parties in different electoral districts. And that, as a next step, we can predict the ranges of likely mandates. So this would now be getting into the Estonian electoral system. So I'm not going to be diving too deep into this. But basically the plot on the right-hand side of the screen is that you have columns, which are the parties, and you have rows, which are the electoral districts. And the bottom row is compensation mandates, which is a separate thing. So this is something that you can't simply just add to this. Compensation mandates co-vary with the district mandates. But this is not, technically too important here. But the way to read this this plot is that there's a different number of mandates in different electoral districts. So the biggest one is the line number 4. So this is 16 mandates that are given out in this biggest district. The smallest one is Lääne-Virumaa down here, which is just 5 mandates. And now you can see that, for instance, in case of Harju and Raplamaa, EKRE, the first column, our far right party, stands to gain 2 mandates with 100% certainty. 100% certainty means that we run 3,000 simulations of elections, and EKRE gets 2 mandates in all 3,000 of them. Now you see that the third column is a little bit off. So if I remember it correctly, it was like 98.2% likelihood of getting the third mandate. So in 98% of simulations, EKRE gets 3 mandates. And then in about perhaps 1 or 2% of simulations, EKRE actually gets 4 mandates in district mandates in Harju and Raplamaa. And so this is how you can read it. And this is something which I must say the campaign managers and politicians have been extremely keen on taking a look at, because it allows you to identify battleground states where certain mandates are up in the air. It allows you to indicate whether let's say, for instance, Social Democrats have next to no chance of getting a mandate in Tartu City or Jõgeva and Tartumaa, but they could go for one in Ida-Virumaa, which is a little bit better. So it allows you to allocate your resources. For instance, Keskerakond has in Harju and Raplamaa, they have 1 mandate, 1 shore mandate, shore in quote unquote, and then 1 mandate as a coin flip. So this is where you can probably, with a little bit of effort, you can improve significantly your chances moving away from coin flip, getting closer to shore one. So that's how it can be actionable. And then, of course, the next step is that we can take these distributions, the mandate distributions across all of these different simulations, and feed it into a final simulation of where we can simulate the majority coalitions across different parties. And we can say that, okay, Estonian parliament has 101 seats, so the simple majority would be 51, but nobody in the right of their mind would go and try and set up a coalition of 51 mandates, because that would be a water-thin margin, and you would probably get slaughtered sooner rather than later. So at least 53 is good for majority. You would probably have to go for 55, 56 to maintain control over the parliamentary commissions. But the model allows you to estimate the likelihood of all of those options. So I can just set the cutoff to 55 and see what is the likelihood of certain combination to get there. And on that basis, I should say that right now, 3 months away from the election, Estonia is looking forward to pretty much a hung parliament. If you know the Estonian politics, then there are 2 big wings, and then they are pretty much dead at 51 mandates. So which is the distribution median down here. It gives you the ranges, 90%. This is the way it works is that you have the party mandate distributions here, and then what you're actually looking for is the joint distribution of certain combinations, and then that allows you to get a pretty good idea of where you stand. So I guess that was the quick rundown, the overview of what we've done. So I'm happy now to take the questions. So maybe Thomas, you can take over that part.
Cool. Yes. So thanks so much for that overview. So yeah, next I'd be really curious to hear more details about the technical side. What were the technical challenges? And yeah, so I'm glad to have Alex here. So Alex, maybe you can introduce yourself and talk a bit about your experience working on this project as the PyMC Labs side.
Yes. So hello, family, everybody. You may have heard Thomas talk about someone called Alexandre Andorra, who did the introductory course with him. Well, that's me. So nice to meet you all. And so been working here at Labs since the inception, and I've actually in my previous life worked a lot on political science, and today is the day where that degree actually pays off. so I've worked actually my first loves regarding Bayesian stats were trying to do electoral forecasting in France, which is the country my passport is originating from. And so I've worked a lot on that, and during that process I also started a podcast all about Bayesian inference called Learning Bayesian Statistics. So go ahead and listen to it if you are curious. I heard it's really good. And regarding actually today's topic, I have at least one episode already, episode 57, where I actually talk about the different models that I use for forecasting French presidential elections, so you can go there. I'll copy paste the link. And also I have an episode with our Pope from Bayesian Stats, Andrew Gelman. I think it's episode 59, where I go with him through the model he did for US electoral forecasting. So that's that, my background. And then, so let me dive a bit, I see one question here from Micha that I address, and then I can go a bit more into the technical details. But basically, so Micha is asking, how do you choose whether it makes sense to add interaction to model? Do you start with all possible interactions? You do not. If you do that, your model will explode. Actually, your computer will explode. No, it will not explode, but yeah, don't do that in the sense that it would be backwards to what we usually recommend. So basically, we often talk about the Bayesian workflow, and the idea of the Bayesian workflow is always start with the simplest model possible. Because what you want is like in physics, or it's like in a lot of science, is you want to have the simplest explanation possible. So you try to trim down your model to the simplest building blocks possible, and then you only add things to it if you have to, because that makes the model more complex, more prone to overfitting, and then it's harder to debug. Also, if you start with all the interactions, well, then if the model doesn't work, how do you know which interaction is actually not working? So don't do that. Instead, use your domain knowledge. So, and that's actually what Tarmo did. Here, I mean, I tried a bunch of interactions, but ultimately Tarmo made the decision because he has the domain knowledge. And actually, I used an interaction that didn't make sense at all for electoral forecasting. I think it was age and gender or something like that. And then Tarmo told me, yeah, actually that interaction, I mean, it does work. The model works and gives you an estimate, but I cannot really make sense of that. So let's remove it and just use, I think, gender and education. I think these interaction, yeah. So yeah, here it's just like simply put, use your domain knowledge and what you think about the phenomenon scientifically, what makes sense, like, does it make sense that people based on gender vote differently if they have a different education? Right. So yeah, that's that. So that's that first question. And then, so yeah, I'll go into Thomas's question, which were the main difficulties. So of course there were a lot, but I would say just to highlight the two biggest ones were, first, when you use multinomial models, you have the model is unidentifiable by definition. So you have to use priors and you have to use constraints. And so the way you guys usually are used to that is called reference encoding. I'm not going to dive into that, but that's also called pivoting. That's one way of doing it. That's the classical way. In this model, we're using something really new that was developed. That's the baby of Adrian Zabelt. And so he came up with that new distribution called zero-sum normal, which is actually a very good name because it's a multivariate normal distribution which just sums to zero across one axis, and that makes the constraint that you want for these kind of models. I'm not going to dive into that. It's fairly technical, but that's actually really fascinating. So if you want that, it's going to be episode 74 of the Learning Bayesian Statistics podcast, where I interviewed Adrian, which is actually really rare. He's someone who doesn't like to talk, so like take advantage of that. But yeah, basically we used that new distribution, and actually the project with Tarmo was really pivotal in that sense, because thanks to that project we worked a lot on that PR and merged the PR also greatly thanks to that project. So now you can use PM.0 normal everywhere, even when it's not needed. So that was the first technical difficulty, but that was really great to work on that, because then it makes the model way faster to sample, and also in my opinion, honestly, way easier to interpret, because the zero-sum normal makes every parameter in reference to the average, so the global average, instead of making all parameters in reference to one category, the pivot category, which here, when you have political parties, is not clear. What's your reference category? It's like, why would you take one party instead of another? If you have a placebo, for instance, then yeah, it makes sense to take the placebo as the pivot. But most of the time, actually, you don't have a natural pivot. So that's one difficulty. And then the other one was after post-stratification. So Tarmo went into explaining post-stratification at a high level. If there are any more questions about that, I can dive a bit deeper. But once you have your posterior samples, we did post-stratification to basically debias the estimates, because they are based on polling data. And Estonia has really great census data, so then we could do state-of-the-art post-stratification on that. But then your model is aware of the demographics we talked about. So like to specify an individual, you have to specify all the demographics, right? But sometimes, often you're actually interested in a broader stratum of the population. So like Tarmo could be looking at the models and being like, okay, actually I want to look at that district, and I want to look just at Russian people, people who identify as Russian and who have high education, but all the other demographics, so age, gender, and other stuff I don't remember exactly, I don't care about that for now. So like, just give me the posterior estimation for what Russians in that district with high education think about that issue. And that was actually a bit trickier than it sounds, to like then aggregate basically these results from the model. A lot of indexing going on into the background, which is actually a big part of modeling. Before you, like when you go into Bayesian stats, you don't really know that indexing is going to be a big part of your life. So yeah, basically that was a lot of that, but then it gives you, once you get there, it gives you like the ability to do exactly what Tarmo wanted, which is like, okay, just let me look at any strata, any stratum of the population I want to look at. So that's that. To answer a question, Thomas, and then like if there are any other questions or else, let's continue.
Maybe I can chip in here and say that pick up just what Alex was saying. This proved to be this was from the get-go. That was a really important thing, that we didn't just want the granular data. We wanted to be able to aggregate across the dimensions, and just like Alex was explaining. And yes, this is something that when you get into the Bayesian modeling, then a lot of time for of what you do is ends up being setting straight the indexes and working the dimensions and seeing that something has gone awry somewhere again and fixing it all. But this, I just want to underline, is something that makes it really easy to work with and really useful. Because in many cases you actually are not after the most precise, smallest nugget of information. You want to generalize over different dimensions, and that's what we did. There was another question about the visualization. I mean, Thomas, you can take this as well, certainly maybe from the PyMC Labs side, but here in this project, we ended up doing the visualization. So if you see the screens, then that was done by us.
Yes. Yeah, and I got really excited when I saw that we built these dashboards ourselves as well, and Streamlit is like a great technology for that. And it's often too easy, I think, and a lot of the examples like just show you posterior distributions, and that's the end of it. But when you apply these models in practice and you want them to have real business value, it's often so critical to how you present this and making all the insights that the model can provide be available to people who do not have a PhD in statistics. And yeah, these dashboards are amazing for that. Definitely something also where just on the PyMC side, we want to make more improvements and tutorials on how to do this yourself. We can help you with that at labs. And yeah, but maybe Tarmo, if you wanted to do a quick demo that we can actually see it live in action, that'd be really fun.
Yeah, I can pull it up just a moment. So let me stop one share and go for another. So that should be it. No, still. I think somebody from the PyMC Lab side has stopped the share.
Yeah, 1 second.
So I can't change the share.
Interesting.
Stop the share.
Okay, now we can see.
Let's see again. So I'll try and pull up the other. I'm still I think you still see the presentation slides, right?
Yes, correct. So no, now we saw localhost.
No, I think yeah. Yeah, I think that was the
Streamlit. Okay, that's then let me pull this one up. Okay, now this should be the right one, yeah?
Yes.
Okay, so just a couple of comments. So the way it works is that obviously it doesn't sample live. So sampling the model in this form would takes about 25 minutes on the M1 silicon. If you're using Intel, then it would probably take you an hour or two. But in about 20 minutes, you can sample this. Then what we do is that we write the posterior into the netcdf file and then load it to the Streamlit. There's a little bit more hacking involved with the, like Alex was saying, with the indexing and coordinates, but nothing too technical. But just to get you an idea, so this is it's a pretty big and complex model. So the posterior, when you write it into the netcdf, ends up being about 300, 400 megabytes, depending on your choices. So we managed to squeeze it down a bit so that it could be fit into GitHub. And now this is this running live. So I can change the district. I can choose the different facets. Say I'm interested to facet by the education. Let's say I'm just interested in males. So there you go. So it all works very, very smoothly. So it's then we can go into the mandates, like I said before. So this is where you can, be very precise with this. Say what is the likelihood of those, and then the final one would be the collisions. Like I said before, like 51 mandates is the bare minimum. 56 is what you would normally need for running putting together a stable collision. And out of these 3 parties, there's a 0% chance by the model's estimate to get to 56 mandates based on these distributions. So now let's add one more party and see if that would work out fine. Yeah, with this party, we're 99% there. So let's say if we want to see if we want even more overlap, say what's the chance of getting 60 mandates? So this would be 62.2%. So yeah, I think this is it's a pretty good view of how well this runs. Again, I must say we're really happy. So you can it's really flexible. It can be pushed into cloud and then shared with whoever you want to share it with. Like I said before, we can replace the party preference with any other question. So yep, I'm happy. It seems to run good enough for me.
Yeah, that looks really cool. How long did it take you to build that?
Well, there's a bit of back and forth, bit of trying different options, ways, but you know, Streamlit is a great tool. So if you know how to work with it, pulling together a dashboard like this from Streamlit side would probably take you half an hour. Now, formatting the data and you know, fiddling with NetCDF and all the dimensions is a different thing. So that will take a little bit longer. But it's a very basically it's a very simple code, and I could of course use some of the stuff that we've done before, but it's pretty smooth and quick.
And making the plots also takes quite a lot of time in my experience. Like the good, like finding good plots. Yeah.
Yes.
Yeah. Exactly. Yeah. Which plot do you show is like, and which library are you using here? Is it Plotly?
No, this is Altair. So this is that has the best. Yeah. It's basically a wrapper of Vega Lite.
Yeah. Okay. And have you thought about like also? I know you have some maps, right, of yes. Estonia. Do you already have that for that model? Because I think that would be like really amazing for like visualizing the details, especially because the model knows about the geographical structure of Estonia.
We haven't put it into that model, but yes, in different places we've used also Altair has the interface with GeoPandas and then very flexible ways of modeling or displaying the geospatial data. And there's a lot more. So it's a really powerful combination that we use throughout our workflow. This was just a very basic demo.
Yeah, and that also like, I mean, if you wanna extend this model even more, you could make the GP also look at geospatial covariation. Yes. Right? It's like so. And actually, if people are interested in that, we have a blog post on the PyMC Labs blog that talks exactly about that, like geospatial GPs, and that was put together by Luciano Paz, and like he goes into the Raven dataset, which probably you guys know about. It's very common, but instead of looking at these counties in a discrete way, which is what also we're doing here in that model, it looks at counties in a continuous way. So that way you also model the covariance, the geographical covariance. And so I think here, like you could have like, you know, the mothership of GPs, which not only looks at covariance through time, which is already what you're doing, but also looks at covariance through space. And like it's like covariance through space-time.
And actually, Alex, if you check on the GitHub where you still have any access to there's a branch where we did add that. We did add the covariance of time and the regional GP, and there's actually one bit added to the model. Now it's aware of the within the units, within the regional units, it's aware of the percentage of urban versus rural population, and it uses this data. So we are constantly adding things, iterating with the model, and this is coming back to the point I made before, that we were lucky to get a very firm foundation for the model, so that it's easily expandable. There's one more question that I can take from Scott, which is, does the forecasting take into account the policy differences between parties? No, this is not something we've coded into the policy. This is coming back to what Alex was saying before. This is part of the domain knowledge. So we know what parties go together. You could do that, try and make it's. You can train the model with covariance between the party preferences, saying that if one party support goes up, then the other co-varies with it. So you can make inferences based on this, but we haven't put that into the model itself. So the parties are the party ideologies are not part of the model. There was a question before about the GP and making it timer, where there's a danger of getting very technical with this if we decide to take this, but I'm happy to talk about that on a general terms, or Alex, if you want to talk about it in a more detailed way, then we can, of course.
Yeah, no, you can introduce the like the general idea, because like this is I love GPs because like yeah, they are so versatile. And like as you were saying, like now you have a GP through space time. Like somewhere Einstein is really proud of you, Tarmo. So it's like soon, like you're gonna be able to model relativity effects on Estonian politics soon. So it's coming soon. It's gonna be part 2 of that seminar.
Yeah. So expanding universe of Estonian politics. Yes, the fundamental point why you would want to use GP there is that if you want to use data, you would normally want to use a lot of data so that the model could learn. And we ended up using 6 months worth of data. But the downside of this is that if the model is not aware of time, then it takes all the variance that's within the data to be being simultaneous, so that there's a within the same moment the support of a certain party can vary a lot, while it actually is a variance over time of people's preferences or people's party preferences changing over time. So what the GP allows you to do is to teach the model to take into account the time dimension, so that it can still learn the interactions or the effects of the different model inputs regardless of time, but keep track of time. So that when you say that I'm only interested in the current moment, then it kind of winds the data to the point of present moment and gives you the best estimate of today. And of course, like with the point that Alex made in a different context before, this is the beauty of Bayesian models. You can run them backwards or you can run them forwards. Meaning that with the GP, you can run the model estimates to the future. This is probably not exactly what you would want to do for a prediction, because the model is pretty fair with you, brutally honest, and says that the uncertainty gets really high when you push the predictions a few months into the future. But if you're inclined to do so, you can. It's just that it doesn't probably give you the kind of the signal you would be hoping to get. But the point of doing the GP is exactly this: you can still use the historical data without that tainting your present moment inferences. Was that good enough, Alex?
Yeah, I love it. Yeah, it's basically that it also helps you, like, as I was saying, like going from a discretized view of the world to a more continuous view of the world, because often time effects, temporal effects and spatial effects are more continuous than discrete. Basically, that's that. Then the difficulty with GP is how do you fit them? And that's also where the magic of the PyMC team goes in. Like, because already with the GP module of PyMC, you can fit GPs in a really reasonable time. Like, as you were saying, like you fit that GP model in 20 minutes on a laptop. It's like
no, not on a laptop. On M1 iMac. Unfortunately, I have Intel laptop, nice. So that would be fitting it like for 2.5 hours. But
if I had M1, your laptop, yeah, my laptop.
If I had M1, so probably yes, but
yeah. So like, but yeah, that's already amazing. And then I mean, then afterwards, here you don't seem to need it, but then if you have really big data or huge GPs, then you would look into GP decomposition, and that's the kind of algebraic tricks that we actually do often in PyMC Labs, and like we actually love doing that. So if you guys are looking into GP decompositions roles and need help, feel free to reach out. It's usually our meet.
Yeah, right now we're using pretty much out of the box GP in our model. This serves our purpose as well. But yeah, the point that Alex makes is a pertinent one. It can get very complex if you want to push it further.
That's what I love about the story and Bayesian modeling in general, right? You start with a simple foundation, and this is often what we help clients with: is build something that is really solid, which is often, I mean, even though the model is simple, it's quite difficult to get something that is that robust. But once you have that foundation, you can develop that model into all kinds of directions. And sometimes we do that. Sometimes the client's able to do that themselves. So Tarmo, like out the GP stuff by himself. And that's always exciting when people are set up to succeed and just push this forward in the impressive ways as you have done. And then, yeah, like build a model that by now is like really fairly complex and models a lot. Maybe as a last question, is there anything that you want to add to the model at this point? Like if you had, I don't know, 5 years more modeling time, what is the model that you would actually build?
Well, 5 years is a long time, so the PyMC will be different in 5 years. This is actually a good point. If you rewind for a moment 5 years back into the past and say that what would you have thought 5 years ago is possible to do, then there probably would have been very few people who would have guessed that in 2021 you can do stuff like this. So this is a difficult thing. But right now we're working with I briefly mentioned before properly sorting out the turnout data, because this is something that came up in the Q&A questions as well, that when can we see the performance of the model. So the general election is March 5th next year, but this model does not give you prediction for the outcome of election. It gives you the latent support for the parties in the population, and to get from there to the election result. This gives you preference, but you will what determines the election result is how people behave, and the preference is just one input to this. So you would need to model the turnout, which is a really tricky problem to model. One of the fundamental problems, as Alex is well aware, is that with elections in general, is that they happen fairly seldom. So you don't have, like weather data. You have every day you can validate your model. Elections you can only validate once in 4 years, and then it also unfortunately happens to be the case that every election tends to be unique in a certain way. This is it's a tricky and difficult issue, but we've been iterating, we've been trying a lot of stuff. We finally got a pretty good signal, so now we're trying to integrate that into the model. So that's the obvious one. There are a few other ideas, but the fundamental point is just, as you said, Thomas, that if you do have a solid, well-running foundation, then it can be expanded pretty easily. So there are no shaky and flimsy parts. And I must say, it's a really soothing sight to see, the model sampling and ending clean with zero divergences, everything, all trace plots looking beautiful. I can look at trace plots, for a long time and just marvel how well it goes.
One of the best feelings in the world. Yeah, converging traces. I love it.
Welcome to the nerd world.
So there's a question about Christoph. How well do you think your model can take into account rare events? Of course, you can't, because if something happens which is not within the scope of your data, then the model is blind to it. So you can probably model in certain kind of noise in different ways, but the kind of events that you say, and that's a pertinent question. These sort of things can have a huge impact on the election outcomes, like the immigration refugee crisis breaking up, war breaking up somewhere, that can tip the scales in a major way. And unfortunately, I don't think there's any way, maybe in 5 years you can forecast these sorts of things, but not today.
What if you use like heavy tail distributions? Could those be adding some more like
robustness, probably
probabilities?
Yeah, probably, but then again, still, it doesn't give you a way to predict, the war in Ukraine or which way it will affect the political landscape. So that's a very tough one to do.
Yeah. So, that's a question that often arises, and so nice to see you here, Christoph. By the way, Christoph is helping me on the podcast. So that's where, and it relates to what you said also before, Tarmo, that right now it's like your model is not making an electoral forecast, but with the GP, you can, because then the model is time aware, so you can actually run the GP on the whole campaign. And basically that's what I did for France. So like you're able to give like a nowcast, which is okay, if the election were held today, that would be the result, which is actually what most people do. And then you can run the GP forward, and then the GP can tell you when the election will happen, here is what we think the preferences will be. So if your black swan happens in like far enough from the election, then the polls will be able to pick it up, and your electoral forecast should be fine. The problem is when the black swan arises like really close to the election, but that's still like a problem that can be mitigated in my sense, because like for instance in France you cannot poll starting from 48 hours before the election. So like that would mean that you cannot see the effect of a black swan happening if the black swan happens, let's say 72 hours before the election. But if it happens before that, you'll have polls. Yeah. And if the answer, like if the reaction of the public is strong enough, then your model should be able to update its prior beliefs and tell you, well, actually like opinion seems to have shifted because of that event. And so the results of the election are actually going to be different. And then actually you could do counterfactual analysis on that. I've done that quite a lot on the French side, which is like usually the black swans in French politics are like unemployment rate. And so you can simulate cases where, okay, what if unemployment doubles, or what if unemployment goes down by, I don't know, 3 percentage points, which is a lot. What would happen in the election in that case? And usually the model is able to pick up the difference. But yeah, if it happens like 48 hours before the election, then yeah, like the model won't be able to pick up all the effect, but nobody will. Like, you know, it's just like if it happens just before the election, nobody can tell you what the result is gonna be. And if someone tells you he can, well, he was just lucky. It's just that he made like the right prediction at the right time. But yeah.
Great. Well, thanks so much, Alex, Tarmo, and thank you all for joining and asking so many questions. I certainly had a great time. I hope you did too. Very interesting discussions and really interesting application of Bayesian modeling in PyMC. So thank you all, and hope you have a great day.
Yeah, thank you all. I did have a great time. The panelists were awesome. So yeah, let's do that again soon.
Couldn't agree more.
Okay.
See you.
All right.
Thanks, Tarmo.